is Rydberg-interacting neutral atoms. Actually, this is not my own research. There are all others' works, but it's something that I might pursue to do research in the near future. Okay, so the key word here is neutral atom, and as you know, superconducting qubits and trapped ions are the two leading platforms for quantum computing right now. And here, I will talk about another platform, neutral atom, but using a readable state, long-range interaction. In the past 2 or 3 decades, the ultra-cold atomic gases prepared by laser cooling and trapping has become a very powerful platform to study many-body physics or condensed matter physics. Many beautiful experiments can directly reveal in front of your eyes. For example, the Bose-Einstein condensation and de Gennes Fermi gas. Or one can use standing laser fields to form optical lattice to mimic the electron in metal. And as you know, this is the Mermin's textbook on solid-state physics. It's a Fengmian. And this Brillouin zone can be realized directly by absorption image. This is experimental data. It's very beautiful. And people can tune the coherent interaction to study this so-called mud insulator and superfluid quantum phase transition from superfluid to insulator. Or people can study like the type 2 superconductor, the vortex, precursor vortex in BEC or BCS region. People can tune the interaction between the atoms such that they can form like a bound molecule or like a Cooper pair, and to study this crossover. So many beautiful experiments are realized. And I want to emphasize that in all this kind of experiment, people use atomic ensemble. It's basically a macroscopic scale. There are a lot of atoms in this case, maybe 10 to 5 or even up to 10 to 8. And about a decade ago, people added some new elements. They can use very high numerical aperture objective lens, such that they can have a single site resolving power on individual atoms. So basically, you can study this condensed matter physics based on microscopic atom counting. For example, you can directly measure the 2-atom correlator, that kind of microscopic quantities. And even you can prepare atom in 2 different states. So you can study spin or density or spin charge, that kind of physics very well. And however, in this kind of experiment, because people use optical lattice, the atomic distance is sub-micro distance, around 0.3, 0.4 micrometer, which are still very difficult to individually control and detect, although it's possible. So there is always a desire to go from bottom-up approach. Basically, you want to trap atom by atom. And around 2000, in this experiment, people use a very tightly focused dipole trap or optical tweezer, such that people can trap a single atom inside the trap. Here is the fluorescence. And this kind of a tight trap, the trap volume is very small and the atom density is very high. And if you have maybe 3 atoms inside, 2 of them will collide and cause some collision loss due to short-range chemistry. So eventually, what is left is only either 1 atom or 0 atom. This is called a collisional blockade. And so people try to use some optical technique using either multi-tone AOM, acoustical optical modulator, or digital micromirror, like this laser pointer. DMD device or specialized modulator. Basically, it's a periodical liquid crystal phase modulator or micro lens array. So when you shine a laser into this kind of equipment, then you can form any kind of programmable tweezer arrays like this or this, which allow you to track atom and then study many body physics. And in this kind of tweezer arrays, the typical distance is around 2 to 10 micrometers, so which allows very convenient single atom control and detection. And in this example, people use a specialized modulator. So you shine a light, and then its diffraction light will form a periodical structure around the focal points. And the phase you modulate is just a Fourier transform of the intensity pattern in the focal planes. So you can use Fourier transform to calculate what kind of it's a programmable holography device. Okay, and around 2016, people can use this kind of equipment to trap atom arrays. However, due to the collision blockade, what I said, the average loading efficiency is like 50%. So you can use some technique, the so-called atom by atom assembly. For example, if you use this AOM to trap atoms, and for some sites there are no trap atoms, so you can just turn off that frequency component and then move the other to linear. So you can form a defect-free 1D atom array. And using this specialized modulator, you can trap this 2D array. So starting from some kind of random patterns, and you move atom one by one, and then to form the pattern you like. And even people can use some kind of adjustable lens and to trap 3D patterns like this Paris the tower. Any kind of pattern you want, you can trap. And actually, this atom by atom assembly now it's become quite popular. Many groups around the world are playing with this. And it's an interesting algorithm problem. I mean, you need to use some kind of algorithm to calculate how many moves you need to move the atom to the desired pattern. In here, it's a Mona Lisa微笑. Starting from this, you can prepare a pattern like this. Okay, and so right now, a few groups they can track about 100 to 300 defect-free single atom arrays. And because atom you can choose any two different states to form a qubit. So you can say right now this kind of platform can have the largest qubit number among all the platforms. For superconducting qubits, IBM they plan right now it's something like 65 qubits. Maybe 2025 they claim they might have 1,000 qubits. And I believe very soon people can trap about 1,000 defect-free atom array in a few years. And to form the qubits, atom has some features. For example, atoms are identical. Atoms here in Taiwan are the same as there in United States. And you can take that for granted. You don't need to, like a superconducting qubit, you need to tune their resonance frequency a little bit by some EM field. But for atom, it's, we can take that for granted. And atom can be prepared to have a very long coherence time, at least a millisecond, and with some effort, it's very easy to reach second, even minutes scales. And there are many well-established control technologies which allow you to control and measure the atoms. So the neutral atom platform become a very popular platform recently. And as you all know, starting from like 3-4 years ago, quantum technology become a very hot topic. There are many 4 categories: communication, computation, simulation, sensing. And there are a lot of news every day now. Here, there are always so many news. And actually, the use of quantum mechanics it's been a long history. The so-called quantum 1.0, like in this laser point, it's a quantum wave structure, and basically you design what kind of material and calculate its Schrödinger equation to design its properties. In this quantum 1.0, people, which is already in our everyday life, it's more emphasized on material designs. And in this second quantum evolution, it's emphasized more on the information technology. And as you know, there are many countries throw a lot of money to emphasize this. And for this quantum 2.0, people want to take advantage of many strangeness or quantum weirdness, like coherent superposition, uncertainty relation, entanglement, locality, non-classical correlation into use. And yeah, I believe all of you have this feeling. Quantum mechanics sometimes is very difficult to understand. This is said by Richard Feynman. It's like a Lao口令. It has not yet become obvious to me that there is no real problem. I cannot define a real problem. Therefore, I suspect there is no real problem, but I'm not sure there is no real problem. Yeah. But anyway, the philosophy of quantum 1.0 is like a joke, say, shut up and calculate. But for quantum 2.0, this is the philosophy: shut up and just use it. Don't worry about that weirdness. And based on my personal research in the past decades, I feel that the heart of quantum technology, quantum science and technology, are all here. Actually, I think we want to take some advantage out of quantum mechanics. What kind of advantage you want to take? Like you want to increase your sensitivity, or you want to take some take advantage of complexity reduction, like quantum computing, or you want more security due to some quantum entanglement. And all these quantum advantage comes from quantumness, which are these entanglements, squeezing, superposition, correlations. And actually, if you look carefully, all this relies on very strong and controllable interactions. They play the active role. For example, you want to focus your EM field tightly with atom. And if you use atomic ensemble, you need high optical depths. And sometimes you want to even use many body effect, collective interactions. In optics, you need to use some kind of nonlinearity. Or require very active role, basically interactions. However, in the meantime, you need to fight with decoherence, noise, loss, crosstalk. And so these two things makes quantum technology very, very difficult. And in the end, it's kind of a pursuit for perfection. And people emphasize too much on quantum computing. Actually, I believe this quantum technology will drive all the community, and all community will benefit from these studies. I want to emphasize this. Theoretical study, actually quite mathematical study, on these quantum advantages are very important. For example, in quantum sensing, you use some entangled state like a GHZ state or NOON state and OON state, you can gain some sensitivity. However, there are always noise are always existing, and in that kind of case, what's the quantum advantage you can gain? You want to calculate that even before you do the experiment. So I believe theoretical study on the quantum advantage is very, very important. Sometimes I think it's even important than physical implementation. You want to know how much you can get in advance. And yeah, experimentally, well, this is just what I said previously. You want to precise control your interaction, and you can measure that microscopic object very well. And if you want to keep the particle coherent, and you need to have a lot of particles working in the same ways. So these are the difficulty of quantum science and technology. Okay, now let's back to the topic I'm going to talk about. Neutral atom, actually readable atoms. Readable atoms are atoms excited to highly excited electronic state. It's high principal quantum number, n equal to maybe more than 10. Mostly people use like 70, 80. And in readable state, electrons are quite moving far away from the nucleus. And so their size are quite big. It's like an n square of principal quantum number. And the most important of all is this, that the transition dipole moment, or electric dipole moment, electric dipole moment can be quite large. So if you have two readable atoms, they can interact through dipole-dipole interaction. However, there are some bad effects you need to worry about. For example, a readable atom might spontaneously decay to ground state. Here shows n equal to 30, the spontaneous decay rate to n equal to 1, 2, 3, 5. The spontaneous decay rate. And not just spontaneous decay, the black body radiation will also affect your readable atom because near the n equal to 30, 31, the EM wavelengths the black body radiation may contain a lot of photons, such that there are black body induced depopulation. Yeah, and taking all this into account, so here shows the principal quantum number and the lifetime of readable atom. Typically, people use around 70, 80, so the lifetime is about 200 microseconds. This will set a fundamental limit. However, you can choose n equal even larger. But you need to worry about some technical issue. And around two readable atoms, if they are a few micrometer far away, the dipole-dipole interaction will dominate. And the dipole-dipole interaction versus the internuclear distance, the interaction strength is compared to the ground state atom can be quite large, maybe more than 12 order of magnitude increasement. If you convert that to the frequency scale, it can be around a few megahertz to maybe hundreds megahertz iteration strength. If the iteration strength is large enough, there is an important phenomena later on we will mention many times, so-called readable blockades. If you have two atoms, and then if you excite one atom to the readable state, and if another one is also excited due to the dipole-dipole interaction, it will cause an energy shift, such that the second excitation can be forbidden. This is called a readable dipole blockade. You can only excite one instead of two atoms into the excited state. However, it's within a certain size called the readable blockade radius. And in quantum gate, the control phase gate for quantum computing, we need to take advantage of this readable blockade. Basic scheme is like this. So you can prepare atom in state 0 or 1. For alkaline atom, that can be a hyperfine state. And the control phase gate scheme is like this. You can apply a pi pulse to couple state 1 to state a readable state. You apply 2 pi pulse with a gap inside, and then you apply a 2 pi pulse on the target atoms in between. Why the truth table of this will just like this. It's easy to understand. For example, if a control atom is in state 1, and target atom is in state 0, and this data is of resonance, so pi and pi cause nothing change, no phase shift. However, for this target atom, it's a 2 pi pulse, and go back to check your radio oscillation 2 level atoms. For 2 pi pulse, it will change the sign, and so it's a -1. You can consider other case, maybe 1, 0, 1. It should be the same. The most important one is this: if both are in state 0, and this pi pulse, it will cause a phase change -1. And due to the readable blockade, because this eta is at excited state, then it causes nothing change. So it's also -1. So 0, 0 is -1. 1, 0 is it's also -1. 1, 1. If both are 1, 1, then both laser field are of resonance, so nothing changes. So phase is 1. It's a control phase case with a universal phase shift of EI pi. And based on this control, also called a CZ phase gate. Just apply 2 Hadamard gates on the target qubits. This part. Apply Hadamard gate is just a 50-50 mean speed, or pi over 2 pulse, and the truth table will become 1, 1, 1, 1 diagonal, 1, 1 of diagonal. So it's control not phase gate. Yeah. So the important point here is actually readable blockade. And this idea was proposed around 2000 by many people: Peter Rowe, Lucan, Roston, and so on. And yeah, it has been realized after a decade by Saffman and Anthony Broadway's group. And for many years, the gate fidelity are around 0.5 to 0.8. So compared to superconducting qubit, they are not so attractive. However, very recently, the Harvard's group actually they just reduce the laser phase noise. It's just a technical improvement. The fidelity can go all the way up to 0.997. And actually, based on Saffman's calculation, the fidelity should be high up to 0.999 in the basic scheme. So yeah, in 2018. In 2019, they realized control NOT gate and 3-qubit TOFI gate with this fidelity. And the important development is this: around 2000, Manuel Endo's group, actually he was in Lucan's group, then moved to Caltech. Then he used alkaline earth atom, the strontium, which allowed easier laser cooling to very cold temperature, and because it's hyperfine. Nuclear spin is 0, so its energy level is really simple. So it's easy to prepare an atom to a single Zeeman state. So they can obtain the fidelity up to 0.99. And so now this platform become a very really popular now. More and more groups actually they start their new project. And for these readable quantum gates, there are many different reasons to cause the infidelity. for intrinsic gate error, there are two main mechanisms. One is due to the lifetime, finite lifetime, the readable state that I just mentioned earlier. And the other one is the so-called imperfect blockade. Although I say if one is excited to readable state, another should be forbidden. However, there are always a certain percentage of probability they can be excited, and so there are some parameters here. Omega is just the laser field you use to try readable to excite atom to readable states, and the lifetime of readable states. And this B is the dipole-dipole interaction strength. So you can play with this. Experimentally, you can play with laser intensity, or the interaction can be tuned by either distance between atoms or which state, which principal quantum number you excite, and either, yeah. So you can see here, if you excite to the higher principal quantum states, and then you don't need to use very short distance between atoms, and then the fidelity can be high. However, there are some technical difficulty. Once you excite to very, very high principal quantum number, the energy level they are very congested, so it's very easy to be affected by stray electric field of the environment. So basically, people mostly they choose around here, the n equal to 75. And then you can optimize this. You can optimize these two equations to find out the optimized laser field and the lowest infidelity or error of the gate. So actually, there is a lower bound once you choose a certain parameter set. And suppose you can make this smaller and smaller at the cost of how precise your technology is. And in the end, you will meet some technical difficulty. Okay, and those are just intrinsic error. And as I said, for almost 20 years, people are still limited by technical norms. And here shows readable excitation. You can use, for cesium, you can use a direct 1 photon excitation or use 2 photon, either through 6P or through 7P. Depends on your lasers. And atoms, although they are cold, but they are still moving around, even though it's a few microkelvin. And if you shine this laser to excite that, there are some Doppler shift, which will cause phase fluctuation. And so the finite atomic temperature will still cause some infidelity or error. Here shows the 1 photon excitation scheme. -3 means the error is 10 to -3. And if you use this 2 photon scheme, because the Doppler shift can be cancelled to some certain extent, so it can be better than the direct 1 photon excitation. This kind of experiment is actually quite tough. Laser need to be very stable, very narrow line width. Intensity need to be very stable, and pointing stability need to be very stable. And also, if you use the 2 photon scheme, intermediate state still have spontaneous decay, so you need to choose a 1 photon detuning. And ideally, you want to have a higher power such that you can choose a large 1 photon detuning, so that the intermediate state spontaneous decay will become less. And also, you need to keep your environment, magnetic field, electric field, very small. So yeah, this study was performed around 2018 by a friend, Anthony Browe's group. So in that study, they identified that laser noise is the current limit. So Harvard's group, they improved the laser performance such that they can get better coherence time between ground state and readable state. Before improvement is like this. After laser improvement is like this. So based on this, they can prepare entangled state between GR and RG, which this is called bare gate It's just a test how good you can prepare the coherent superposition. And so they can get a 97 fidelity. So this gives people confidence that Rydberg atom platform, they are just limited by the technical issue so far. And yeah, to be honest, any kind of quantum experiment, they are tough. It's not that you already say, oh, you have fidelity finite. It's just like a precision measurement, like an atomic clock. You need to worry about any kind of noise. For example, what I say, Doppler dephasing, lifetime, laser noise, and it not just in the interaction. You also, for measurement, you also need to worry about a lot of stuff. How precise you can prepare your population in state 0 and 1. State 0 is not just one state. It's maybe f equal to 3, n equal to 0. There are still 6 states nearby. You need to use optical pumping to prepare population into that state. How precise that can be. And how precise you can detect this atom. It's really in this state. It's called a preparation and measurement error. In the end, all of this will affect you. And in sometimes people normalize this part. It's just consider the pair interaction part. And how precise you can control pi powers, 2 pi powers. It's pi or it's 0.999 pi. There are a lot of technical issues. And then based on 2018 experiment, then Harvard's group realized this control nut group with high fidelity. They also important feature of a Rydberg atom is that it's a long-range iteration. In a demonstration experiment, people just prepare 2 atoms. But ideally, you can prepare many atoms, and if you shine this atom, the nearby atom will experience that dipole-dipole interaction. So you can actually build a so-called multi-qubit gate, like a TOFI gate. It's a control NOT gate. For some calculation, you don't need to rely on just 2-qubit gate. You can just directly use multi-qubit gates. Or you can actually use a 2-qubit gate to model this multi-qubit gate. But as you know, each gate has a certain fidelity. 0.99 times 0.99, you will degrade. So sometimes you can directly use multi-qubit gates. And this is the Caltech's experiment. They use alkali earth atoms, the strong C atom. Also, they can see much better ground state and Rydberg state coherence. Why they can do this much better? Because for alkali earth atom, there are 2 outer electrons. So they have spin triply, spin singly state. For spin singly state, it's a metastable state. They actually choose this as ground state and they decide to Rydberg atom. And also, alkali earth atom, you can use the narrow transition to laser cool that to sub-recoil temperature, which is like 0.2 microkelvin. So just by those reasons, they can get an even higher fidelity. And to be honest, these are still not enough. And so you can imagine that in the short term, FICO will make even colder temperature using some more sophisticated laser cooling scheme. And then people can make more stable lasers and use even more intense lasers such that you can choose a larger one-photon detuning to minimize the intermediate state spontaneous decay. And to be honest, I haven't talked about many issues. Like you trap atom inside the tweezers. Atom still can experience some AC, inhomogeneous AC star shift. And for Rydberg atom, if you use a ray detune for ground, it can track ground stable. For Rydberg state, it will be an anti-trap. So during the gate operation, actually right now people turn off the trap, so that you are not going to do a long gate operation. So in the end, people need to build a blue detune or even so-called magic wavelength traps, such that the AC star shift of ground state and Rydberg state will cancel each other. it's just like there are no trap there. So you can minimize the decoherence. So there are still a lot of improvement. And if you want to get dramatic improvement, maybe you need to go to cryogenic trap. As I mentioned, black body radiation will affect the readable lifetime. For example, at room temperature at n equal to 80, lifetime is 200 microsecond. If you can call that to liquid nitrogen temperature, it's about a factor of 2 increasement. But this is still not large, even for zero temperature. It's about a factor of 3 improvement in the lifetime. Actually, you can choose circular readable state. What is circular readable state? The quantum number is NLM. So L equal to n minus 1. So the electron will moving very far outside. And for that circular readable state, you can go to check it. The spontaneous decay rate is very long, as long as like 30 milliseconds, much longer than this, factor of 100. Yeah, but some people are already, so actually, circular readable state has been trapped recently. Some group start to work on this. However, it's not so easy to prepare atom into this state. So there are still a lot of effort people need to put. And even you use the current atom, the current readable system. The basic control nut scheme, its fidelity should as high as 0.999. And that level has not been reached yet. And you can choose some advanced scheme, advanced gate scheme, to cancel, to minimize the blockade error. You cannot minimize spontaneous decay. Spontaneous decay, you just need to choose N larger or colder, or circular readable state. Yeah. However, there are some people like this guy. They propose some advanced gate scheme. I don't have time to introduce this. They can get the fidelity down to 10 to minus 5. So there is still a lot of room. People can improve. And in the end, what I mentioned that the qubit number is already on the order of a few hundreds, which is the largest among all platforms right now. However, if you want to really evaluate how the performance of a quantum computer, some people define different quantities. For example, quantum volume. So qubit number is circuit width. How many operations you can do within the coherence time is a circuit depth. And not just this, the fidelity need to be high enough. Otherwise, the overall performance is still bad. Even though you have maybe 1,000, 10,000 qubit, but if the fidelity is low, it's useless. So in this definition, qubit number and this circuit length, circuit depth, you can conduct your quantum operation with a small gate error. Yeah. And so right now, this is the table for trapped ion and for superconducting qubits. Some they can claim, IBM claim that they have 64 recently, and Honeywell recently they have claimed they have already reached 500. IonQ even claimed they have 4 million. And for neutral atom, people have not reached to this level yet. But there are still, as I say, there are still a lot of room to improve. And here is a comparison for many platforms, superconducting qubit, already 65 qubit, trapped ion. The full run, although it can be like a 79, but the real qubit number they use is something like 30 only. However, their fidelity can be high. Both IonQ and Honeywell, they make a very good computer now. And as I emphasized, neutral atom, the qubit number is the largest now. And very soon I'm sure it can reach to like 1,000 qubits. However, there are still many room to improve the fidelity. Yeah. Yeah, but this is what I just said. And so for neutral atom platform, the whole cycle looks like this. You load some atom with some random pattern, and then you do rearrangement, and then you apply laser light to perform target operation, and then you use fluorescence or some other methods to measure the states. To be honest, at this moment, there are only like 2 or 3 qubit, 2 or 3 atoms that has people apply that kind of gate. Yeah. There are still no demonstration like the trap ion. It's very complicated algorithm yet. And for all the platforms, without error correction and fault tolerant computing, you cannot say it's a universal quantum computer yet. And people call this kind of regime the noisy intermediate scale quantum error quantum device, the NISQ device. And people are asking, okay, there's still a long way to go for error correction, the real universal quantum computing. But with this kind of machine, what can we do? Cannot outperform classical machine with this kind of quantum device. People identify some problem like quantum annealing or quantum approximation or the variation of eigenvalue solved for molecule energy level. And some of them there has been demonstrated, although it's still not outperform the classical machine yet. And for readable atoms, some group identify this platform may be more suitable for this kind of combinational graph problem. It's a mathematical problem. However, I want to emphasize, even at this regime to outperform classical machine, they are still very, very tough. You still need a qubit number like maybe 1,000, 5,000, that kind of order. The fidelity may be at least 3.9. And for readable atom, people identify this problem should be quite suitable for this kind of platform, which is called a maxima cut or maxima independent state. Basically, you have some points or vertex here. You want to cut a line and then to categorize atom or vortex into two groups, and they have no their age will be the largest, or this one is better to say. You find some independent state, for example, red and white atoms. They don't they have no near neighbor to each other. And maxima independent state, there are many this kind of independent state. And the maxima independent state is the independent state which has a maximum number of state. And for readable atom, due to the readable blockade, so you can say within a certain distance, the other atom cannot be excited to a readable state. And so here just shows if you shine a laser light to excite atom to readable states, the atom are readable states, and you will be naturally prepared to the independent state. If you are, to be honest, I just looked about this a few days ago. So if you are interested, you can go to look at this reference. And yeah, so right now these are based on the so-called gate-based universal processors. But you can categorize the work into two parts. the digital or gate-based quantum computer. Actually, people do more work on this, the analog processing. Basically, you don't individually control each atom. You don't control individual atom. You just prepare many atoms, and then you engineer the Hamiltonian by the laser intensity, by the laser detuning. And this Hamiltonian, they have double interaction. And then by engineer this parameter, you map this problem. But actually, it's directly a many-body problem. And in some example, this many-body problem may map to the mathematical problem, like a graph problem. So that allows you to do either many-body physics or computational problem. And for readable platform, there are many beautiful experiments. It's been done within 3 years. For example, these are experimental data. They are not simulation. So you prepare atom like this kind of atom, and then you shine laser light to excite that to readable state. And for the dark side, the reader atom will be repaired when you turn on the trap. And what are left is the ground state atoms. So you can see some place readable. It's kind of a spin model, and you can model the quantum IC model, or if you excite atom to 2 different readable states, you can model more complicated spin model, like a so-called XY model, and you can see it's a ground state or what's the steady state, and you can even study its dynamics. For example, you can control the laser parameters. So many beautiful experiments has been done by this platform, and there are even more exciting experiments within this year. You can prepare atom in this kind of hexagonal called Kagome lattice. What is shown here, the green side is the readable atom. These are just simulation, but this kind of simulation has been realized recently. And with different laser parameters, different kind of state can be formed. And so, yeah, you can study different quantum phases. And this is a very recent experiment. So they prepare this kind of very strange crystal structure, and they play with the Brachet radius, the double interaction strength, such that if the Brachet radius divided by atomic distance, lattice distance, and only one of the atoms excite to the readable state, and yeah, for example, in that. And this is a so-called quantum speed liquid, because there are many possible combinations like this or this due to the Brachet. So actually, it's a many-body entangled state. And many years ago, in high-DC superconductivity, Anderson or Cui Zhangqi, they are talking about RBB bond. This is a kind of realization of this RBB model. And this quantum speed liquid, many people in that field, like Wen Xiaogang, they are talking about this for more than 2 decades. And these are experiments. So right now, it's kind of, to some extent, it's kind of realization of either the quantum speed liquids or resident RBB model. And to some extent, this kind of topics is also related to the fault-tolerant quantum computing, because in that kind of scheme, people prepare some kind of topological protected states. Yeah, this is paper just come out within a few days, and I heard in some academic social network, people are very excited talking about this development. And also Wen Xiaogang. Okay, So we are thinking to build such kind of platform to do our own study within 5 years. Basically, what we need to build a basic system, and then want to improve all these issues, and then get a good control NOT gate. Maybe we will realize more advanced gate schemes, and then we will try to pursue for that kind of a simulation work. And in the end, we may choose some kind of a great problem to really attack it. Yeah, it's still in planning. And actually, in Europe, about the same time, the EU they slow like Taipei 3.5 亿 to University of Stuttgart, Timmermans group actually the PI under him. They want to build this kind of system too, and they just start this project. And actually, there are 3 world famous groups like Anthony Broadway's group in CNRS. They start a company, Pascal. And in Harvard and MIT, Lucan Vladimirovich, Marcus Brenner group, they initiate another company called the Q-Era. In California, there's a new company with Ying-Cheng and Goshkov as scientific advisor. They initiate another company, Atom Computing. All 3 are based on this readable atomic array. And yeah, so that's all of my talk. So welcome to join our group. We are lacking a lot of manpower and working on these new topics. And in my group, we are also working on cooperative effects, superradiance, subradiance, also content enhanced metrology by photon pairs. Okay, thank you.
Okay, any question, comment?
System you mentioned involve many atoms. So could you say a little bit about how to do this and how do they calculate the interaction between so many atoms and how do they involve in this communicated system?
So it's basically based on this Hamiltonian. The atom, they will couple atom from ground state to excited state to readable states. And if they are in readable state, different readable atoms can interact through the dipole-dipole interaction. It can be effectively right down to like this. This N, they are readable, population. So basically, you convert this atom to a very simple model. You just consider, in this case, you just consider 2 states, ground state and readable state. And if they are in readable state, they have interaction. And the laser may this readable state occupation number. Basically, it's a 2-level system. It's a very typical 2-level system, but they have interaction.
There are 3 companies already.
Yeah.
Could you describe how advanced they are in their products?
Well, I don't know. They don't have any product yet. You go to their website. But my point is this: I don't think in the end they will sell this quantum computer. I guess they will sell the enabled technology, like how do you control these atoms by laser light. You definitely need some kind of multi-channel modulator or something like that. I believe in the short term they will sell that kind of products. Or like Honeywell, they already make the ion chip-based ion chip. In the short term, I believe there are many groups in the university. They might don't have fabrication equipment to do that, so they may purchase some maybe custom-made chip from the Honeywell. In the short term, I believe this kind of related technology will allow them to earn money. Just like a coherent system, there is a company called Co-Quanta. They are selling the magneto-optical chip. They are selling a BEC system, and I know there are some group they already purchased that in 成功大学 Professor Guan Peichen, he already purchased a mark system. And like in M Square company, previously they are selling lasers. Right now they made an atomic clock, a portable atomic clock. They can sell that already. And that, you know, there are many space projects. NASA will cooperate with that kind of company. So they can start earn the money already. Like IBM Q. I see that their advertising skill is very good. Like NTU physics. we give them 2 million, 20 million every year, right? Just for training. So, yeah, I believe in the short term, the related technology will allow them to earn money. But after 10 years, I'm not sure who will purchase a quantum computer from that. But you might purchase a coherent system from that to do some research.
All right. Is there any fundamental issue about scaling up with
Fundamental issue.
Yeah, is there any?
Yeah, I think, yeah. To be honest, the long-range interaction that we mentioned, it may be good, it may be bad. Like superconducting qubit, you have the 2 qubits nearby. You can introduce some interaction and entangle them. But for readable atom, due to the long-range interaction, if you will automatically entangle with many atoms. So I'm not sure it's a good thing or bad thing. I mean, for some application, it may be a good thing. But if you want to very precise, well-defined entangle which 2 qubits, that may be a problem. And to scale up, there are a lot of technical issues I didn't mention. Like, although you have many traps, but due to some abbreviation, 相差, optical abbreviation, the trap might be not so uniform. So their AC station might vary one by one. And then if you apply laser lights, this may be 0.999 pi pulse, that may be 0.98 pulse, pi pulse. That will be a problem. But people will try to improve that the technical problem. But to be honest, at this moment, I don't see any group demonstrate large scale operation yet. But because the fidelity is not so good. So, but fundamentally, I'm also thinking about this. If one day our capability is high, what kind of how can I do like this quantum relations for like ion chip? Ion chip, they have all-to-all connectivity, but readable atom might not be able to do that. Yeah, that is something I'm also asking myself.
Okay, so you specify your readable state by the principal quantum number, right?
Yeah.
Which might be good for alkali atoms, but for the other type of atom, like the alkali Earth you mentioned in the latest experiment, right? Have you ever considered to control the angular momentum state? Or is there anything good or bad?
Yeah. Yeah, like I say, this circular readable state is actually the biggest angular momentum state. In this example, the advantage is the long lifetime. But I know there are a lot of error state there. But like a D state, it might have some angle dependence. That might complicate your quantum gate operation. However, it might be good for quantum simulation. Like what I said, XXY model, that kind of complicated spin model. You may simulate that kind of very exotic spin model. Yeah, but for computing, I guess the philosophy, people try to keep system simple. Yeah, but for simulation, you can play with any kind of exotic states.
Okay, so I'm following the other guys' questions because you mentioned you try to improve on current experimental standards. So have you ever done the SWAT? On the
Swap gate.
SWAT. Like weakening stronger point.
Swap gate.
Compare with other.
Yeah. You mean SWAT gate? SWAP? No.
No, SWAT.
SWOT analysis.
Yeah.
Okay.
I think that's the point.
Well, yeah. Based on my current, my previous experiment, as I say, emphasize, all these kind of quantum experiments are very tough. And I personally, I have some experience on quantum memory, which we make the world record on efficiency. So all you have to do is you need to do everything, every detail, very, very carefully, in order to make your system very good. However, you will also need some good idea. That's the weak part. So we collaborate with Xie Mingxiu in Honghai Quantum Computing, and also Junda, also Professor Zhang Yanghao who is good in many-body physics. And Junda and Xianghua, they are good at atomic physics. And Xie Mingxiu, they are good at computational physics. So we want to combine all these manpower, try to choose some problem to attack. But it's just, we're just in the stage of understand all this. So I don't know I have what strength I have. Yeah, but based on my previous experience, I'm a little bit confident on the experimental part. We definitely will make that better. Like our quantum memory, we estimate that it can be that good, and then during years efforts, we really reach that. So in this case, I believe not just me. I mean, other people will soon reach 0.999 fidelity. If it's possible, then it's possible. It's just a matter of time. But sometimes it's not so quick. That means like what I said in Rydberg-Adams case, around 20 years, only like maybe 2 or 3 groups they are working on around this direction. But other people say it's only like 0.7 fidelity. What's the problem? Maybe there's some big problem there. But you just need to check everything carefully, and the French group, they really check that carefully, and then they say the laser noise is the current limit right now. But yeah, and then Harvard's group improved that. But to some extent, you may ask the same question. So now laser is very good. What's the next problem? And there are a lot of effort you need to put that. And anyway, it's not easy. It's tough. But if you don't do that, you will just sit and watch other people very beautiful stuff. So we need to start from somewhere.
Okay, any other comment? If not,
Sorry.
if not, let's send the speaker again. And we will have the tea time right after. So.